So tonight's last call for Lab 6, need to have that put to bed by tomorrow. I know many of you have already done that in anticipation of having something else to do tonight with your time, so hope you guys have fun at Fenway, those of you who are sophomores. So today and again next Tuesday, we're going to be looking into how to make a higher performance computer than the one that we've built so far. So we're going to switch back to hardware and architecture for a little bit, and it's actually sort of fun. We'll just get started on this journey. It turns out that the processor that's embedded in the laptop in front of you uses some of the things, uses the techniques we're talking about today, and then there's another 30 years of architectural development that are all attempting to achieve higher performance. And performance is measured in a fairly simple way. It's the number of instructions that complete each cycle, or how long it takes to complete an instruction. So that's mostly we don't care about latencies of how long a particular instruction takes to execute. We're much more interested in the throughput of the processor, which is measured over some span of time. On the average, how many instructions will it execute per unit time. And there's sort of two things that are opportunities that are available to us. One is, so we have a numerator and a denominator. So this is basically a way of just millions of instructions per second. Maybe that should be billions of instructions per second in the modern world. So we can sort of take how many cycles it takes for a particular to execute a particular instruction, and then we can worry about how fast those cycles are. And so those are sort of the two knobs we can twist. With our RISC simplicity, we've designed an architecture that really has no trouble executing an instruction in a single cycle. It's simple enough that it's easy to, we don't have to run 12 clock cycles to do all the 57 steps necessary to execute an instruction. The instructions were chosen to be simple enough that a modest piece of hardware can execute a complete instruction every cycle. And you say, well, how can I do better than that? And the strategy, once you get to your instruction sort of working in a single cycle, is to think a little bit about how could I do 2 instructions in one cycle or 4 instructions in one cycle. And in fact, a lot of the transistors that you own in your computer are devoted to the so-called multiple issue machines, the idea of being able to execute multiple instructions at the same time. Now, if you think about your programs, you can see that's a challenge, because if you write an instruction that leaves something in R2, and then the next instruction goes off and references the value in R2 and does something more to it, you can see that there's a lot of dependencies between instructions, one right after another. And so executing them in parallel is a challenge. And in fact, there's a lot of work in the processors to find enough to do in order to keep the processors, all the functional units in the processor busy. And in recent years, the hardware types have once again sort of punted it to the software types. And instead of trying to build one CPU that executes one program really, really fast, for reasons of both power dissipation and architectural complexity, and the fact that the traditional single-threaded architecture sort of ran out of steam about neat new ideas to make them run faster, we now tend to sell you 2 or 3 or 4 cores, or soon to be 8 cores, soon to be whatever in your processor. And it's really up to the programmer to figure out how to to sort out assignments for each of the processing cores. So multiple issue is alive and well, but it reached sort of a plateau, and then after that, the way we get more performance is simply having many CPUs run in parallel. And we'll talk about the architectures for doing that after we finish the pipelining. So a week from today, we'll be talking about that. But today's task is to figure out how to make our clock cycle faster. We've got a basic strategy. It executes instructions. We have this big piece of logic. We want to, if you think about, if you look for the TPD as you sort of go through the entire picture of what happens after the rising clock edge, think of all the things that need to happen in terms of executing an instruction and the different hardware blocks involved. And then you're all ready to store the result in the register file at the end of the cycle. You look at that and you say, okay, that's sort of, I'm going to look for the longest path through this little maze of all the operations that have to be performed. And that will tell me how long it will take to execute the instruction. What are some of the big things that we have to think about? What are the big investments of time? Well, whenever we have to fetch something, go to a memory. So we have the going to main memory for the instruction, going to the register file to get the ALU operands, or going to main memory towards the end of the cycle in order to finish off a load or a store operation. Those are expensive. Main memories are slow, so our timing budget is gets a little bloated because of that. And not for the register file, which is small and reasonably fast, but for these memories in a modern architecture, we would actually have not talk directly to memory. We'd in fact talk to the caches, which we would expect to have performance on the order of the performance of the register file. The other blocks we want to think about are the big arithmetic blocks. So we've we actually have these big ripple carry adders, both to increment the PC, to perform the branch offset calculation, and to go off and actually do arithmetic on data that the programmer is trying to manipulate. And those ripple carry adders are actually slow, and some of the design project handouts talk a little bit about how other adder architectures that are probably 3, 4, 5 times faster in terms of the actual nanoseconds it takes to do a 32-bit addition than the simple adder architecture that we use. But nonetheless, in the timing diagram, we sort of have to look at this and say, well, the ALU is sort of in the way here. So if we think about instructions that sort of hit as much, what's the longest way we can go through this diagram? Not all paths are possible, right? You could draw some paths through here that aren't actually taken by any of the existing instructions. So, but if we think about existing instructions, we can imagine that a load, we have to fetch the load, we have to fetch both the address, we have to fetch RA from the register so we can go off and then in the ALU add it to the constant to compute the address that we send to the memory, and then the memory data comes back through the WD mux and into the... So that sort of touches a lot of the big blocks. So we would expect load to be, one of the instructions that's setting the clock rate. Here's the load relative, which computes the address in a slightly different way. So we sort of end up going through the branch offset calculations instead of, and then we don't use the ALUs for much of anything except to pass that result through. Thing to keep in mind is this axis is not to scale. I mean, what I really should do when I saw the memories, or even if they were caches, is they'd be much longer if the time scale is vertical. So, thinking about how do we speed this up? Okay, we know what order the calculations need to happen in. We have a whole series of blocks where the output of one block is fed to the input of the next block. And you look at this and you say, okay, we know how to do this. In fact, I don't know why I devoted 2 lectures to this. Seems like we could get done in a couple minutes. We know how to make a piece of logic run faster. We pipeline it. We take all those slow blocks, all the washing machines and dryers, and we put them into separate pipeline stages. And for a particularly slow block, we might choose to interleave them, right? We could say, oh, fine, we'll just, we'll make 2 ALUs and run them, sort of half a cycle off from each other. And, we could use our interleaving strategies to make things sort of as fast as we want. So it seems like this should be pretty straightforward. So what is the big deal? Why aren't we sort of done after drawing some stripes across our unpipelined diagram? Well, the first thing to notice is that the beta is not a big piece of combinational logic, right? There's actually state elements here. And what that means is that there is some memory in the system of the effect of previous execution. So the instruction ahead of you and that came before you has actually changed the state of the machine in such a way that when I'm the next instruction and I execute, I actually have to take into account changes that it made to the state. If you think about a combinational diagram that where we pipeline a bunch of combinational blocks, so we have these diagrams that are and we want to pipeline these guys. You know, when we did this, we were making the assumption that all the information that this guy needed, okay, would be passed along the pipeline like so, and these guys could, without any reference to what the downstream guy was doing, could go off and start on the next calculation. Well, that's not true anymore. If this guy is writing into the register file and this guy is reading from it, right, then we sort of have to, there's information that's flowing not strictly downstream in these simple diagrams. So if you think about what wires sort of go backwards in this diagram, right, you can think of the branch offset wire, you know, working here in this looks like the second stage, passes information backwards up the pipeline, if this is the pipeline diagram. You can think of the register file, you know, the W data, which is actually almost the last thing, you know, the write data for the register file, which is almost the last thing that gets computed. Actually gets passed way back up there and changes the state that was actually used very early on in the execution of the next instruction. So those are problems, okay? And we're going to spend a lot of time dealing with the consequences of those problems and seeing if we can still get the benefits of pipelining while shuffling our feet, doing our jig as fast as possible to make sure, and this is sort of a basic requirement, that we'd like to keep the semantics of the, you know, of a program the same. You know, the goal here is to say you don't have to rewrite all your programs if they worked fine on the unpipelined beta. In general, our goal is to have them work fine but more quickly, unchanged, to work unchanged, but and correctly on the pipeline beta. They just run faster. That's our goal, right? So Intel would not be able to sell new processors, you know, as well as they seem to be able to if, in doubling their speed, they also said, and by the way, every program in the world has to be rewritten. Right? That wouldn't be a practical thing for them to try to get away with. Okay. So our strategy, like most pipelining things, is to take the expensive things in terms of time and put them in their own pipeline stage. And now we're going to spend the rest of this lecture and the next lecture dealing with, oh my goodness, that changes how things execute. What can we do to save our bacon? And we'll actually take our fairly simple machine and add a bunch of complexity to it in our attempt to build a high-performing pipeline processor that meets this final constraint. So our ultimate goal, just to give you a sense of where we're going to end up, you know, at 1:55 next Tuesday, is that we're going to build a 5-stage pipeline. So we break the execution up into 5 distinct phases. The first phase is we fetch the instruction. So that's step 1, is to take the current PC and go off and get that instruction from main memory. So that first instruction fetch from main memory is in its own pipeline stage. The second thing we're going to do is we're going to decode that instruction, and for instructions that need operands from the register file, we're going to go fetch them from the register file. So step 2 of the operation is basically to get the necessary operands for step 3 of the execution of an instruction, which is to actually do whatever we're supposed to do with the 2 operands. Okay, so we've already on to step 3 here, and once we have the result from the AOU, for certainly the load and store instructions and the LDR instructions, we are then, we have to put in a step which is not needed by all instructions, but assuming that we use the same recipe to execute each instruction, we have to leave room in our recipe for loads and stores to go take the address computed by the AOU and to fetch the corresponding data, or to write new data into the location that was addressed by the result coming out of the AOU. And finally, when we're all done, for pretty much everybody but store, our job is to take whatever result we've ended up with through this up to now 4-stage pipeline, or 4-step process, and in the 5th stage, we write that information back in the register file. So this is the so-called classic 5-stage pipeline. So almost any book in computer architecture will basically, through various paths, explain to you how a 5-stage pipeline works. Now you look at, you scratch your head a little bit and say, okay, but I read just the other day that there's a 23-stage pipeline in my Intel processor. I mean, you know, how does that work? And that's an interesting question, one that we're not going to talk about here. But if you are very interested in that sort of computer architecture idea, there's a neat course, 6823, which actually talks about all these gruesome, wonderfully complex, fascinating details about how these high-performance processors work. And you learn a lot more about what all these pipeline stages are devoted to doing. Okay, so we're going to start off modestly. We're simply going to build a two-stage pipeline. We're going to have one stage be the instruction fetch, and the next stage be the execution of the instruction that was fetched. And you say, okay, so that's two steps. So what's magic about this in terms of why is this performance better? The thing to realize, of course, is that while I'm executing one instruction, I'm fetching the next one in parallel. So the savings I'm getting is that the time it takes to do the instruction fetch is no longer added to the time it takes to execute an instruction. In other words, in terms of in our timing budget for how long a cycle takes. So we're going to have, in one cycle, we will in parallel both fetch an instruction and execute the one that we fetched in the previous cycle. And that means that our timing budget really just has to take into account the worst case of these two steps. It doesn't have to imagine they both have to happen in one cycle. They happen in separate cycles. So we're going to get a speed up out of this. We're going to be able to take the cost of the timing of the instruction fetch out of the budget for a single clock cycle. Everybody sort of understand the idea? So what we're going to do is we're going to add some registers here. So you can see this big gray stripe, and we're going to add some registers here, where the stripe crosses information that's flowing down the page. And you sort of look at this and say, fine, so to execute the instruction properly, I'm going to have its PC plus 4 because that's used by various instructions. LDR, or if I'm doing a branch, that PC plus 4 will need to store it in the register file. So I'm going to need that piece of information, and I'm certainly going to need the 32-bit representation of the instruction itself. I can hardly execute the instruction without the binary representation. And so that's, those are the registers we add here. And in general, one of the things we'll be doing as we do pipelining is adding more and more registers. Now, you may be a little puzzled about why we didn't put a register there. After all, it's a line that crosses, our pipelining arc. Aren't we supposed to put a register every place? The trouble is that information is flowing backwards up that line, right? So, in some sense, that's and there's a real problem there, and we're about ready to talk about that real problem. So the fact that there's no register here should be at least raise a warning. Either Chris has really porked it today, or there's probably something we need to deal with, because there's something that's happening in this stage that will affect what's happening in that stage, in the earlier stage. And so let's talk about what that is and how we can deal with it. So here's a picture of a pipeline diagram for the two-stage beta. And when we introduced these, I made a forward pointing to this lecture with the idea that pipeline diagrams will help us understand very nicely how a pipeline processor works. Remember how a pipeline diagram is organized. We have each of the pipeline stages as rows, and then as columns we have successive clock cycles. And we can tell for any particular clock cycle what each pipeline stage is working on. And so if I think about, I'm just going to follow execution here. So I fetch the ADC instruction. So that happens in cycle I. And in the next cycle, I'm going to be executing the ADC instruction in the execute stage. And while that's happening, I will be fetching the next instruction, the sub-C instruction, from memory. So those two things are happening concurrently in a single clock cycle. Notice that instructions basically sort of move diagonally through the diagram. So as we think of the instruction as it goes through stage by stage by stage, in other words, it's moving down row by row by row in a pipeline diagram, that motion happens one stage per clock cycle, so that the instruction effectively just marches diagonally down in our pipeline diagrams. And if all goes well, each instruction will basically just march through, and if we had a 5-stage pipeline diagram, we would have 5 different instructions all being executed in different stages of their execution, all in the same clock cycle. And if the gods were with us, maybe our processor would run 5 times faster. right? If we could equally divide all the delay that we need to invest in the execution of an instruction, if we can divide it equally into 5 chunks, then our pipelining will actually get us quite a speed up. We're not going to be quite that lucky, but that's the basic idea. Okay, so this all works great. Everybody's going, great, this so far, Chris, no problem. Well, I hinted that the problem had to do with branches, and so what I would like to do is to now consider the execution of a program with a branch in it. So here's a simple little loop, an add, a compare, then a branch back to the beginning of the loop. And let's see what happens here. So we start off fetching the add, that's great, and then while the add is executing, we fetch the compare, and while the compare is executing, we fetch the branch. So far, so good. And now the branch is executing. So this means that at this clock cycle is when we're actually thinking about we actually have the information from the register file. That's what, in the execute stage, we're going to go off and fetch RA, and the branch instruction wants to look at RA to see if it's 0 or non-zero. And so the decision about whether we're going to go back to the beginning of the loop or execute the XOR is being made in clock cycle I+3 for the first time through the loop. Okay, the difficulty is that if we're going to take the branch, do we want to execute the XOR? Right? No, that's, in general, if we're going to take this branch, we're going to go back to the beginning of the loop. It's a 3-instruction loop. We shouldn't really be executing the XOR until we exit the loop. It's the first instruction to be executed if we do not take the branch. However, what's our pipeline done for us? It's already gone off and fetched it. Right? Because it was busily doing its job, okay, before the branch decision was made. And so it's saying, okay, I'm getting the next instruction, yeah, XOR, XOR, XOR. And you're sort of going, wait, stop. We may or may not want to execute that XOR. So what are our choices? Okay, so we'll make a little menu of choices and investigate the consequences of making the choices. One is we can so-called annul the instruction. So that's a term you see in pipelining literature a lot, the idea of annulling an instruction. That means turning the instruction into basically an instruction that has no effect on the state of the machine. So even though it says XOR, what we're going to do is say, never mind, we'll throw that instruction away and do nothing. We're going to execute a no operation. Okay. So, and we could, now there are different ways we can do that, and we'll have a very simple way that turns out to serve us well. You can turn off worth in the right, so, the things that cause the state of the machine to change, you can just basically disable them, and now the state of the machine doesn't change, so it's like the instruction was never executed. So annul the instruction and say, don't execute the XOR. Okay? Or we can program around it, right? We can basically put explicitly an instruction that does nothing, so you can go ahead and execute it. It's fine, processor, execute it. I know that you are going to execute it. I'm going to plan for you to execute it. And since I don't, I'm going to put in a no operation so that no op is, what is an example of a no op? It might be something like this. Add, R31 to R31 and stick the result in R31. Any instruction with a destination of R31 doesn't change anything in the machine, right? I mean, that write gets thrown away in the register file. So, I could follow all my branches by an instruction like that. Or, since the compiler knows that instruction will be executed, maybe the compiler can put an interesting instruction to be followed there, knowing that each loop actually has one last instruction it executes before it jumps back to the beginning. So the branch is not the last instruction at the bottom of each loop. It's actually the second to last instruction, and the compiler knows maybe I can figure something clever to put in that I really want to have executed if I'm going to continue the loop. So branch alternative 1, annul the instruction. So when I take the branch, what I'm going to do is simply replace that XOR as it moves from the instruction fetch. So I sort of know the branch decision right here. So as this instruction would have normally moved through into the instruction register for the execute stage, as it does that move, if I don't want to do it, I'll replace the instruction I fetched with one of these magic no-op instructions. Okay. So you can say, well, okay, that gets the job done. The thing to keep in mind is about 14% of the actual executed instructions, and this is the spec mark is a sort of famous set of benchmarks for measuring processor performance, is that about 14% of actual executed instructions are taken branches. So that means that if accounting for now the branch instruction, right? That means about 12% of the total cycles would be annulled. So that would mean that this particular solution, although it keeps the semantics correct, is pissing away 10 or 12% of the performance of your machine on the, sort of, if you went off and did a bunch of measurements, this is sort of what our benchmarks tell us you would measure. Okay, so you can say, well, my machine is running somewhat faster. On the other hand, I'm throwing away some of the extra performance by, getting some percentage of the instructions to work less well. So keep that in mind. That's alternative one. And it's executed very simply in the hardware. If we choose to annul an instruction, if we say down here, we're doing the branch offset calculation, we're looking at the output of this NOR gate, we do want to change the program counter to actually jump to the branch destination. When we do that, we know we're no longer going to be executing the fetched instruction, because that's the instruction that we're going to throw away. We simply use a multiplexer and we put in a different binary representation of one of our no-ops in order to rewrite the instruction that we fetched into something that will have no effect on the state of the machine. So the hardware is not very complicated. It just has mostly a cost in performance. Okay, well, you say, well, SMOP, Chris, small matter of programming. Why, instead of adding hardware, why don't we tell the software guy to go off and simply put in no-ops? Well, now your programs are longer, so now all of a sudden you have all these no-ops filling up your memory, and so instead of synthesizing them in hardware where needed, we put them into the actual program itself. So a little less hardware, but the cost is my programs are now 12% longer than they were, which is, that's a non-trivial cost, particularly on, cell phones and watches and washing machines and things like that. These costs add up. Okay, so we could do the same thing in software, and now we're getting into the fanciful part. I'll take into account that, in fact, I'm going to move the add that was at the top of the loop. I'll do it once up here, but then each other time through the loop, I'll make that the instruction that will be executed after I do the branch. And so I'm thinking about this rewrite that reorganizing of the instructions to put something useful that can be executed in the branch delay slot. That's what we call the instruction, okay, that comes after the branch is being fetched, and the instruction in the branch delay slot will actually execute it and tell the programmer, don't put in no-ops, see if you can rewrite the program to put in something useful. And you say, okay, well, if you think about how this works, that would mean there's one extra add somewhere in here, and we have to add an instruction to undo the effect of that add. It's sort of a pain, and often you can't really do that, right? So the chances of rewriting the program this way get a little small. Yes?
On the previous slide, the branch enrollment hardware?
Yep.
Don't you have the same problem with setting that MUX because you have information flowing backward?
Well, what we're doing is we're making a decision in this stage about what to do with the instruction that's currently being fetched. And so long we can get the signal here with enough time to rewrite the instruction right before the end of the cycle, it'll work. Okay. Okay, so the final solution is to actually, instead of rewriting the program, is to do something here that we say, look, this program was written to execute this instruction when the branch was taken, but if you don't take the instruction, if you don't take the branch, annul this following instruction. So we can get more and more complicated about sort of trying to instruct the machines about when to execute the instruction in the branch delay slot and when not. The thing I should point out is that all these modifications, aside from the addition of the no-ops, all these modifications to the, whether to execute the instruction before or after the branch, work well in a pipeline processor, but that means that the same program doesn't work in an unpipelined processor, which, when it takes the branch, simply isn't looking at the next instruction at all. So we're a little nervous about some of these alternatives because they actually, even though they make our pipeline processor work, the same program will not give the same results in an unpipelined processor. Okay, so in general, in our implementation of the pipeline beta, we're going to choose to keep the semantics of the programs the same between unpipelined and pipeline. So we're going to choose to do the annulment in hardware. So we'll add the little bit of hardware so we don't have to rewrite any programs, make them longer, and we'll take that small performance hit. So that's going to be our choice. So just to back up a little bit, here's our 5-stage pipeline. Notice that every time we take a branch, we have to throw away sort of the instructions in earlier stages because they relied on thinking that I'm going to continue execution, and the branch changes the execution order. So that means wherever the branch decision takes place, in the case of a B&E or something, we're making a decision on the information coming out of the register file, which means that we only have to throw away the IF instruction, the instruction in the IF stage. However, if we made our branch decision later, so for example, if we had a branch instruction that compared the output, the result, used the ALU to do a subtract and find out if one register was greater than another, and we made a branch, we could say branch register A greater than register B, if that was an instruction in our machine. If we chose to take that branch, we now have 2 instructions to throw away. And if we had a sort of a branch of memory 0, we could test the results coming back from memory, okay, we'd have lots of instructions to throw away. So this notion of a branch delay slot and throwing it away, these start getting more and more and more expensive. Okay, the later the branch decision gets made, the more instructions that follow the branch are in the pipeline and have to be flushed or thrown away or annulled, okay, if the branch changes the order of execution. And in fact, a lot of the hardware that you buy is devoted to very clever solutions. Okay, it says, well, I don't know, I'll speculatively have 2 programs running now, one of which has that instruction executed and one of which doesn't, and I'll sort of keep track of sort of several generations of speculation about what's actually happening in your program, and when I finally make the decision about which is the right speculative execution, I'll throw away the old execution. So one way to use a lot of extra functional units is to have them guessing about, did I want to do that XOR or not? And one branch will assume I did, and the other branch I assume I don't. And when I finally make the branch decision, I can choose which execution branch to do. Okay, so speculative execution is something that your processors try to do very well, but they end up throwing away some percentage of their work because they've invested in executing multiple paths to your program, only one of which will be the true path once the decisions get made. Okay, so deep breath. We did we added that one pipeline stage up here, this one here, and then we had to deal with this backwards wire. Right, this idea that we're making a branch decision here and doing some computation that affected what we wanted to do in the earlier pipeline stage, and that caused us to add some hardware and do some annulment and deal with that. Okay, let's go ahead and continue our exploration about adding additional pipeline stages. So let's add a few more. Let's make sure the instruction memory, the register file, the ALU, and the load and store data fetch are all in different pipeline stages. So each of our piggy blocks, our time-consuming blocks, is now in a separate pipeline stage. Our hope is to get, well, if the gods were really with us, we'd get a 4x improvement, but maybe we'll get a 2.5 or a 3 times improvement in the cycle time, and that's still worth doing. Okay, so just as we had to deal with this information flowing backward in the pipeline here, in this particular picture, notice that the register file is really being treated, the read ports are up here and the write port is down here. It's the same register file, but conceptually, the writes are happening way down here in the last pipeline stage, while the reads are happening in a much earlier pipeline stage. So there's an implicit transfer of information from this stage, when we change a register, to this stage when the register is read. So in this case, the backwards wire, okay, has to do with the contents of a particular register in the register file, the one that's being written down here. And if I happen to have, at some earlier point, been reading that register hoping to get a result from some earlier instruction, it may or may not be in the register file. It depends whether that instruction has finished its progress through the pipeline stage and has actually gotten to the point where it's writing the information in the register file. Yes? Yep.
After a branch, but meanwhile with your hardware you've implemented an annulment. won't that essentially destroy the program?
Yes, so I mean the compiler has to know what the hardware is doing. And in general, most modern compilers make a very conservative assumption that work on every implementation, say of an x86 processor. It's possible to tell the compiler that you know this will be executing on a very particular processor. The modern compilers know a lot about the details of each generation of Intel processor, and they'll actually work on instruction scheduling, knowing that you're doing. The Intel hardware is designed to work correctly, even if you get the instruction scheduling wrong, but it will work much more efficiently if the instruction schedule that the compiler compiled actually is running on the processor that it knew about. So in general, you don't want to come up with a hardware implementation that simply breaks. Okay, you were trying to get higher performance, but if you break all the existing programs, no one's ever going to buy your higher performance machine. So in general, you shouldn't make, the compiler writers and the hardware implementers shouldn't make inconsistent choices about, for instance, how branch delay slots are dealt with. Okay, so we're hoping for a reasonable improvement in the cycle time, maybe 2.5, 3, I don't know. We'd have to do some of the arithmetic carefully. But right at the moment, we're interested in what other semantic changes has this cost us. We have to worry a little bit about now, are there things like branch delay slots that will cause the programs to suddenly execute incorrectly unless we go fix them? So we're going to get a start on fixing that. We're thinking about that now, and then in the next lecture we'll deal with all the things we don't get to today. Okay, so notice what the pipeline, so it makes pretty, so the two operands are being fed into the ALU, the write data is being pipelined so it can be fed to the memory at the right moment. The instructions are certainly being pipelined down so that each stage knows what its operation should be. Notice that the PC+4 value is also a piece of information that has to be sent through the pipeline, because actually it's not until we get right to the end where we might have to write PC+4 in the cases of branches and jumps and things like that into the register file. So what the registers here represent all the information that's needed for the successful execution of the remaining stages for a particular instruction. So we have to make sure to pass all this down. So we've actually, these are big 32-bit registers. And so, the register cost in this is non-trivial, but our hope is that our processor will be noticeably faster. So in the modern world, we have a lot of transistors in our budget, billions and billions. Let's spend them on making higher performance machines. That's sort of what we're thinking. Okay. And this is just talking a little bit about what's contained in some of those pipeline registers. So how does this work? Well, as usual, we'll start off with an example showing it working really well. And so here's a program. And there's something interesting about this program. Notice that all the registers that are being changed by each instruction, so the add C is changing R2, the sub C is changing R3, the XOR is changing R1. Notice that I've changed R2 here, but none of these instructions refers to R2. Right, so in some sense, even though this instruction will eventually change the contents of R2 in the register file, when the add C instruction gets to the write back stage, none of the earlier instructions care about the contents of R2, so that will be fine. So in fact, this particular set of operations works well. It's at this point, magic point here, right at the end of cycle I+3, at the end of the write back stage, that the add C finally will update the contents of R2, but none of the mul, XOR, or sub C used R2, so we're all set. Right? I'm sorry? Oh, I'm sorry, but it needs to be able to read it in the register file stage, right? So it's okay for the mul to be in the instruction fetch stage. Good catch. Thank you for correcting my thing. So the use of when does the mul instruction use R2? When it needs to get the contents of R2 from the register file, right? And that happens when the mul is in cycle I+4, when the mul is in the RF stage. So happy with that? Did I take my foot out of my mouth? Good. Okay. Alrighty. So far, so good. But of course, there's an example that works less well. So here's an example that works less well, and it's pretty easy to see what the less well part is. The add instruction is writing its destination register as R3. Here's the add instruction in the write back stage. That means the write to the register file happens at the clock edge that's the boundary between I plus 3 and clock cycle I plus 4. And that means these blue shaded guys here, starting at this point, is when the contents of R3 are actually available out of the register file. So it's at this clock edge that the register file actually gets updated with the result of the add instruction. Where does the first place I try to read R3 from the register file? Well, the compare instruction, the RA register for the compare instruction, in fact, is reading R3. And that means, if we think a little bit about it, that I need to be able to read R3 from the register file in that cycle. Okay? It is available here. I'm trying to read it there. If I look in the register file, the number I'm looking for isn't there yet. So can the compare instruction successfully complete its RF stage operations? The job of the compare instruction in the RF stage, or put it the other way, the job of the RF stage when it sees the compare instruction is to say, I'm going to go get the operands. And the operands are the constant 100, appropriately assigned extended, and the contents of register 3. So that's supposed to happen by the end of this cycle, but I can't do it. Does everybody see what the problem is? I'm looking in the register file, the answer hasn't put out there. Because of the way I've done the pipelining, that write isn't happening until later. Okay. Oops. So I hope I made clear what the problem is, right? I'm trying to get something before it's where it belongs. So now we're going to go through our little litany again. This particular solution, well, just program around it. You know, every time you have a write into a register file, you're not allowed to read it for 3 cycles. Okay. And so we're sort of building a lot of knowledge of exactly how deep the pipeline is into forcing the compiler writer to say, look, you can put a value into R3 or R3. You simply can't read from R3 for 3 more instructions. So go figure out something else to do. Okay. And you start rummaging around hoping you could rewrite the program. Well, almost never can you rewrite the program. You might do a little shuffling, but on a general basis, people write programs to say, look, you know, I'm going to compute something, and then I'm going to use it to compute the next thing, and I'm going to use that to compute the third thing. There's a sequence of operations that tend to depend on what happened in earlier operations. Okay. So we can insert no ops out the wazoo if we actually have to ensure that the add is out of the write back stage before the compare can work. I could insert, you know, 3 no ops in there, and that'll guarantee the right thing happening, or maybe it's 2 no ops, but some number of no ops. Okay. The second solution, oh, well, we're pretty good at you know, faking instructions, these no op instructions. So what I'll do is I'm going to freeze the earlier stage of the pipeline. I'm going to basically prevent it from moving forward. Right, so the compare instruction basically gets stuck in the RF stage until it can get the value it wants from the register file. Meanwhile, you know, the ALU stage is saying, well, give me something to do. And so the compare, which would have gone this way, but I can't send the compare down the pipeline stage yet because I don't have the right operands, we start putting in some no ops, which then, of course, flow through the pipeline. So the so-called data hazard, this hazardous reading of a register file entry that's not there, okay, we could use no ops to solve that problem. But if we were sort of being a little nervous about the no ops being introduced by branches, we're going to be really nervous that, you know, what we're really doing now is spacing the execution of the instructions out. So each instruction has to get through the write back stage before we're willing to let the next instruction get into the ALU stage with the right operands. And so that means that almost all the performance that we're getting out of pipelining, except maybe for the overlap with the fetch and execution, so this will actually end up, for many programs, boiling down to mostly a 2-stage pipeline. We'll sort of, all these no ops. So you actually look at what's finishing up is add, no op, compare, no op, no op. And you sort of look at this and you go, oh my goodness, you know, half of my instructions, you know what, 2/3 of my instructions are no ops. So even though they're running faster, I'm not getting much for it. But, okay, and this is the fun part. When I think about what the compare instruction needs, what is it the compare instruction needs? What's it looking for? The result of the add, the thing that will be written into R3, is that in fact nowhere to be found? Where is that information? It hasn't gotten into the register file yet, but it's actually in the machine. Where is it? is stuck in the pipeline, and in fact is sort of coming out of the ALU. In the stage I'm trying to read R3, it's actually coming out of the ALU down here. So the value I want is there. Okay, if I were only smart enough to recognize that in this particular case I'm trying to read R3, the instruction ahead of me in the ALU stage is actually computing the new value of R3, maybe I'll just sneak and grab that value. I don't have to grab it from the register file. If I'm clever enough, I can actually grab it from where it lives in the data path. Okay, and this notion of grabbing a value from somewhere in the pipeline stage is stuck in the pipeline, stuck in traffic, but I'm going to allow myself to reach down and say, I know where that value is, I'm going to get it. I don't have to get it from the register file. Okay, so what I'm going to do is this little backwards arrow indicates that I can, is called forwarding the value from the ALU stage back to the register file stage. In the case that I happen to notice that the destination register for the add, okay, turns out to be one of the source registers for the compare. So this notion of bypassing, you say, well, isn't this a little complicated, Chris? And the answer is yes, wonderfully so, right? I mean, but we have lots of transistors, and we're desperate to make our machine perform well to get that factor of 3 or 4 if we can get it. So we're going to start adding some more hardware in addition to the pipeline registers to deal with what the so-called data hazards, where I'm trying to get information that's in the pipeline but is not yet gotten written into the register file. So for example, I can make this big sort of complicated equation that says, look, if the instruction, so if the opcode, so compare less than or equal to with a constant, reads the RA register, so this particular opcode knows that it wants the value in this case of R3, but whatever the register number is in the RA field of that instruction, okay, and the result is being computed by the ALU, that's what the second line is, if it's an ALU operation. And if the destination of the register for the operation in the ALU stage, okay, happens to be the register I'm looking for, I can grab the value, and I'll use a big multiplexer here to instead of taking the value that's come through the register file in the A cell mux, I'll simply say, oh, ignore that value. That turns out not to be there, not the correct value to have. I'm going to instead just read it from the output of the ALU. Now, I thought when I first saw this, I said, whoa, this is pretty neat. In other words, I'm actually being very sophisticated about exactly what values are in each being computed and when they're being computed in the pipeline. And if I can, I'm going to take those values before they get written back in the register file and start using them in subsequent computations. So does everybody understand how the bypassing works, why it's getting the correct value? Implementing all this logic that sets the control line, the select line for that multiplexer based on all these conditions. These, you can write logic that computes all of these, is this binary number equal to that binary number, so forth and so on. You can do that, okay. It just, this logic starts piling up. So not only do we have all these 32-bit data paths that are suddenly being multiplexed, but then the control logic starts getting a little bit complicated. And in fact, getting bypass control logic to be correct is one of the favorite pastimes of processor designers. It takes some work to get all the conditions when and where you're allowed to get values from instead of from the register file. But people do it, and their processors run pretty fast as a result. There's an extra condition, by the way, that if add was trying to write into R31, in other words, it was no op, and I'm trying to read R31, do I want to do the bypass? No. So there's these little gotchas where this all sounded great, and then you start taking care of all the stupid little details of, oh, by the way, writes into R31 don't actually change the contents of R31, so we want to make sure it always reads as 0. So the bypass logic equations are starting to get a little complicated, but conceptually you can see what's happening. And similarly, I can perhaps bypass, so here's an instruction that's trying to read from R1 and R2. We see there's no R1 and R2 involved in the ALU instruction, but there is one here in the fourth stage down here, or third stage, I guess, in this picture. But the idea is that this guy's writing R1, I'm trying to read R1, so I can bypass from different pipeline stages. And in fact, for each pipeline stage that's subsequent to the register file stage, there's bypass paths back to the register file. And then increasingly complicated equations, making sure that I'm actually not, if Lamolsi had been writing R1, I would want that value instead of that value. So, it's interesting to figure out how all this works. Okay. So the question is, well, if it's about to be written in the register file, can't we just get it out of the register file? Just remember that the register file write happens on the clock cycle, at the clock edge at the end of the cycle, right? So it's not in the register file until after the instruction has, after this XOR instruction has finished in the write back stage. Okay. Whew. Okay. Wipe my brow. I've talked about this dealing with this sort of state that's being used by subsequent instructions, and making sure that I either get it from where it exists from earlier instructions, or I have to sort of figure out how to stall the instructions until it's available. So we'll keep that in mind over this long weekend, but I'll remind you about it starting next Tuesday, and then we'll finish up our neat exploration of pipeline processors. Good luck on Lab 6. Have fun getting a ring if you're a sophomore, and we'll see you tomorrow in recitation and next Tuesday in lecture.